record again. Okay, so we are recording. So up are the notes from yesterday. We want to touch on a couple trig topics just to finish up. I just mentioned to the class of how to find more lecture videos on trig. I do just want to kind of touch on the key points for using trig and the things you should kind of memorize and how to apply trig. You will be using trig for like the rest of your collegiate career, basically. If you're going to be an engineer or computer scientist, all the way at least through Calc 3, through differential equations, trig functions are going to show up. So I want to finish up just with a couple of topics. Some of the topics we're not going to be able to touch on from this section, and I'll mention those as we finish up. I do want to do, let's see, where's my outline? Here we go. At least one trig problem solving and how to solve trig identities, trig equations. So general things you should know for trig. Anytime you're doing a trig problem, I almost always draw this little reference sheet. And what I like to have handy and visually is our 45, 45, 90 triangle with the side lengths, 1, 1, root 2. Again, easy to remember. Our 30, 60, 90 triangle with 1, 2, root 3 side ratios. I like to have the all seniors take calculus diagram just to let us know which trig functions are positive and negative. And then some of the trig identities. So we didn't get into trig identities yesterday. In terms of trig identities, almost no one has all of them memorized. There's some indifference formulas, there's double angle, half angle formulas, and people will memorize these for various periods of time and then forget them, and then you will always re-look them up once you need them again. So in terms of helping you guys with that, in terms of the minimal things that you should maybe try to memorize to just have in your brains as engineers, as STEM students, I would recommend the first one's the Pythagorean identity. Almost everyone knows cosine squared plus sine squared equals 1. There's other trig identities that we can then base off of that. As STEM students, as engineering students, you are hopefully more comfortable with manipulating trig functions. So if we want, there's like 1 plus tangent squared equals secant squared, right? In order to get that identity, well, if you don't remember it, or if you forget, is it +1, is it -1, how does that work out? At least if you can memorize this one, I can take both sides of the equation, divide by cosine squared, and then come up with a new identity. So all of the Pythagorean identities you can come up with this way. And then the other identity that's really useful to have in the pocket of your brain is at least one of the double angle formulas. And that double angle formula I would recommend is cosine squared x minus sine squared x is cosine of 2x. So the reason it's easy to memorize is because it's exactly like the Pythagorean identity, except with a minus sign, right? So if you can remember cosine squared plus sine squared is 1, and then change the sign, cosine squared minus sine squared gives us a double angle, cosine of 2x. So we'll use this a little bit today. And again, there's other versions of the double angle formula that we can derive, now substituting in this identity. So for example, if I take sine squared, if I solve this top equation for sine squared to get 1 minus cosine squared, and then plug it into this identity, we can get a different double angle identity. So this stuff is all good to have memorized. And then from that, you can kind of build almost any tools you need and come up with them without having to look it up. Of course, being engineers, being STEM students, most of the time, if you really, really need a fancy formula, which there are a few in trig, you can always just look it up. And most of the time, that's perfectly acceptable. The other thing I wanted to touch on, so one of the questions I got from WebAssign was, what do you do with the quadrantal angles? So these are all of our basic angles. And yesterday I did also mention that sometimes this is handy. So pi is 2 pi over 2, is 3 pi over 3, is 4 pi over 4, is 6 pi over 6, and how to count in these fractions of pi to determine which quadrant you're in, what reference angle you have, and then identifying the ratios to evaluate trig. The problem is well, I didn't really mention how do we do these pi over 2 angles or the pi. Because if we want to evaluate trig functions on either of these two denominators, on either of those two fractions of pi, well, our two reference triangles aren't going to work out. So the last thing I would recommend understanding is the use of what are called degenerate triangles. So what is a 0 degree angle or a pi angle? So for 0 degrees, which is of course 0 radians, how would we draw that if we wanted to draw a triangle in standard position? Well, you can kind of think of this triangle here, this pi over 6 side, except we're smashing this side down together. It's going to be this hypotenuse now rotated down on top of the x-axis. So what do I mean by a degenerate triangle? And I almost want to draw this as skinny as possible, because really it's a triangle that doesn't make sense. It's not really a triangle, but we're drawing it as if it were, and just kind of mathematically reasoning what's going on with this triangle. So what do I mean? I mean that this vertical side shouldn't really exist. It's really a 0 length. I want this, our terminal ray, to be smashed on top of that x-axis, which means that this terminal ray and the x-axis are the exactly the same length. I'll just give them both 1. The Pythagorean identity still has to hold. 1 squared plus 0 squared has to equal the hypotenuse squared. So this is our 0 degree angle here, and then from that you can calculate all of the trig functions. Likewise, with a 90 degree angle, be careful with your 90 degree angles. Remember, the angle you make with a triangle in standard position should always be, the right triangle, I should say, should always have its right angle perpendicular to the x-axis. So it's always the vertical side. And so this should be our angle here. But again, if I want this to be really on top of the y-axis, this side should be smashed over. Our hypotenuse should be equal to this vertical side here. So my vertical side is going to be 1. Hypotenuse is always 1. And then this horizontal side is now 0. So this is going to be our pi over 2 angle. And again, sine of pi over 2 now you can see is opposite over hypotenuse. So sine of pi over 2 is 1. Cosine of pi over 2 is going to give us 0. So same thing with pi and 3 pi over 2. Just be careful with the minus signs. You want to draw them similarly, except now the hypotenuse, again, hypotenuse always positive, but the x and y values could potentially be negative. Since this vertical side shouldn't really exist, since we're at an angle of pi, it's going to be 0, but the x side is going to be -1, hypotenuse always positive. So this is pi here. And so now you can compute your trig ratios based off of that. So cosine of pi is going to give us -1 over 1, which will give us -1. Sine of pi gives us 0 over 1. And you can do something similar for 3 pi over 2. So I usually don't draw these in my trig reference sheet because they come up a little less frequently. And if I have to, I can always just draw them and understand how to draw these degenerate triangles whenever I need them to evaluate trig functions on those specific angles. Okay, so keep this stuff handy. Let's go ahead and solve at least one trig problem and then move on to functions. We're not going to have a whole lot of time today since we did have to talk about WebAssign. So we want to solve in 0 to 2 pi. We've got an equation 2 plus cosine of 2x is equal to 3 cosine of x. Maybe we'll do 2 of these. So we'll call this problem 1. And then we'll do one more after this really quickly. So what's going on with these equations? The one thing you need to solve trig equations is that the arguments, the input for all of the trig functions has to be the same. So here we have a double angle, 2x, and here we just have an x. So we need to reduce this double angle down to just a single trig function of x. So we can use that formula that we listed on our other sheet, this cosine of 2x formula that we have. So this is going to be 2 plus cosine squared of x minus sine squared of x. And I would say be careful. Let's keep everything in parentheses because we are substituting out this entire expression. There could be a minus sign or a factor out front that we would then have to distribute. Nicely enough, though, it's just a positive, so we won't have to do any of that work. However, the next step in terms of solving trig equations, it can get a little tricky because there's different techniques at this point. Whenever you generally have powers, squares, and linear terms and constants. So like we have trig functions squared, trig functions to the 1 plus constants. Best strategy is to get all of the trig functions the same. So here we have cosine squareds and sine squareds. It's not going to help us. So we want to convert these sine squareds to cosine squareds. Since, well, I have cosine squareds and I have cosine to the 1, we might as well convert our sines. Easiest thing to do. It'd be harder to convert everything to sines, so we're converting the cosines. And again, mind this minus sign because we are going to substitute out our expression for sine squared as 1 minus cosine squared. Once you have all the same trig function, all the same arguments, now we want to collect all the powers, collect all the terms, put them all on one side. So we're going to have 2 cosine squared. We'll have a -1 and a +2. So that'll give us a +1. And then I'll subtract this 3 cosine x to the left. And now what you want to do is notice that this is something like a quadratic equation. So we can make a substitution and just call cosine of x some function u. And really what we have is 2u squared plus minus 3u plus 1. And so what we want to do is factor this as a quadratic. And it looks like we're going to have -1 and -1. So check that real quick. Our 1 works. We'll have -2u minus u gives us our -3u. And of course, our 2u squared. So solving this, we'll get u is equal to 1/2. We set each term equal to 0. So 2u minus 1 equals 0. Solve that out. You'll get u equals 1/2. Likewise, here we'll get, u equals 1. Which means we now have to solve our cosine of x is 1/2 and cosine of x is 1. And now that we're at this point, we go back to our reference sheet. We want to know what angles is cosine of 1/2 and what angles is cosine of x 1. So different ways of solving this, different techniques, depending on how you want to integrate the pluses and minus signs. I always use the reference angle first. So look back at our reference sheet. We have cosine of x is 1/2. So when we look at our triangles, I can only get a ratio of 1/2 out of these two sides, but I need the cosine, that to be the cosine ratio. So we want this pi/3 angle. We'll have our adjacent over the opposite, or adjacent over hypotenuse. So cosine of 1/2, we need our x equals pi/3. Cosine of x equals 1. This is going to be our degenerate triangle. So anytime you have cosine and sine equal to 1 or 0, it's going to be a quadrantal angle. So we would go back over here and realize our cosine of x is going to be 1 when the adjacent and hypotenuse are the same side. So it's going to be 0 degrees here, or 0 radians. Now, I'm missing one angle. So nicely enough with this one, this is the only solution. Cosine of x is only going to be 0, or excuse me, is only going to be 1 at 0, or, sorry, I guess we should include one more. since our domain or our range for x's includes 2 pi, we can include 2 pi here. We have to include one more value here. So how do we include this? Other things to check now. So we want to check, make sure our sign is correct. So when I say cosine of x is 1/2, it's a positive 1/2. We simply used our reference angle here and said, well, cosine of pi over 3 will give me a ratio of 1/2. We got to be careful about the quadrant though. So that's where I use this diagram here. Pi over 3 is going to be in our first quadrant, and cosine is going to be positive there. So that will give us a positive 1/2. However, cosine is also going to be positive in quadrant 4. So we're also going to need a pi over 3 reference angle in quadrant 4. Sorry, let me put that on the screen there. So that means we need this reference angle to be pi over 3. Using our techniques of counting in fractions of pi, if I go all the way around, that's 2 pi, which is 6 pi over 3. And then we just need to go back one to get this terminal side here. So 6 pi over 3 minus pi over 3 gives us 5 pi over 3. And that's our other solution. Now, this problem, the difficulty in the problem was using the trig identities before you isolate these equations. Cosine x equals 1/2, cosine x equals 1. Once you isolate your trig equations, or trig function is equal to a constant, we then use our reference sheet and our knowledge of trig functions on the unit circle to solve which specific angles. You want to be careful because sometimes once you get to here, there's some extra work to do after this. So let's do briefly one more. If we had just a basic trig equation of saying something like sine of now 2x is equal to 1/2, and let's make it negative. So now the setup is pretty straightforward. We don't have any trig identities to use to get to this point. We have trig function equals a constant. We can go ahead and use our reference information to get rid of our trig functions. The problem is we have this 2x here. So you want to think of this as an angle theta. And based on our reference sheet, again, we're looking for when sine is 1/2. So sine is going to be 1/2 at pi over 6. However, it is a negative 1/2. So while pi over 6 will give us a sine ratio of 1/2, we actually need a negative value. So the quadrants we need are going to be in quadrants 3 and 4. So we need a pi over 6 reference angle in quadrants 3 and quadrants 4, meaning if we go pi, so 6 pi over 6 plus one more, we will have 7 pi over 6. And then the other one we will have, actually, let me just write a new equation here. In quadrant 4, sine is going to be negative. We go 12 pi over 6 minus 1 to give me that pi over 6 reference angle, and that will give us 11 pi over 6. Now, again, let's go ahead and say solve in 0 to 2 pi. Our problem now is that this was our general theta, but we have to figure out what specific x values. And actually, one thing I haven't written is what's called the periodicity factor. And the periodicity factor is this term here. Because sine and cosine are periodic, I could add on 2 pi to any of these angles and get new angles. Typically, those angles are going to be outside of our range of solutions that we're looking for. However, because we've doubled the speed of the arguments, we're actually going to come up with new solutions. So when we divide both sides, we're going to have x is 7 pi over 6, or excuse me, 7 pi over 12 plus pi k. X is 11 pi over 12 plus pi k. So k is going to be an arbitrary integer. I can multiply 0, 1, 2, negative 1, 2. Essentially, all it's saying is as I add on integer multiples of 2 pi, we're getting the same solutions here. But because we had this factor of 2, now what this is saying, I can add on integer multiples of pi and still find solutions to our equation. And since we can add on integer multiples of pi, those still might lie within our range of solutions. So our solution here then is going to be x is 7 pi over 12. And we can add on a multiple of pi. So adding on 12 pi over 12, we get 19 pi over 12. Over here, we get 11 pi over 12. And then if we add on a multiple of pi, we'll get 23 pi over 12. Okay, so just a refresher on that. Again, watch the videos on Canvas and on YouTube to go over more of this kind of stuff in detail if you need a refresher on trig, or stop by office hours. Happy to help you guys and give you guys some practice with that. We only have a few minutes left in class, so we only got about 10 minutes. Let's go ahead and talk about functions real quick. So again, most of this stuff is pre-calc review. We probably won't be able to cover everything in detail. I do want to cover what is a function, because typically I don't like the way it's taught in a math class. So our proper definition is something like a relationship between an independent and dependent variable such that for every value of the independent variable, I'm going to abbreviate variable VAR, there corresponds exactly one value of the dependent variable. This is the proper mathematical definition. It is essentially telling us graphically that a function should satisfy the vertical line test. So if you're unfamiliar with the vertical line test, take a look at the pre-calc lectures I've mentioned. It basically says if we have a graph of some object, if it is a function, then I should be able to draw a vertical line at any point on the graph, and it will only intersect the graph at most once, maybe 0 times. Any graph that has where I can draw a vertical line that passes through more than one point, then in this case, our y is not a function of x. Again, we typically have our x, our independent variable, on the horizontal axis, our dependent variable y on the vertical axis. So this is the proper mathematical definition, but this, being applied math and engineering, doesn't really give you a better sense of, well, you know, how do we use functions in the real world, and how are we using this abstract mathematical language to help ourselves when we want to do engineering and physics problems. So better ways to think about functions. These aren't necessarily proper, but the way I would like you guys to think about a function, in especially for this calculus sequence, is a sequence of mathematical operations, i.e. generalizing our 4 function, maybe 5 function, and then maybe something like here, I'll put it as maybe a little box to the n, exponentiation. So we start off learning mathematics with basic arithmetic, addition, subtraction, multiplication, division. And again, addition's a very natural thing. Well, what is multiplication? Multiplication is just iterative addition. What is exponentiation? It's just iterative multiplication. And so this kind of begs the question, as we do these operations more and more, as I have more additions, or I start to combine these operations, multiplication and then some addition and then maybe some exponentiation, some division, how do I describe that? And that really is what a function is. We want to think of a function, at least for these types of courses, that, well, now I generalize all of these and have a sequence of operations. So for example, we can describe it in words. Take a number, add 2, and then multiply by 5. That would be the function f of x, where x is some number. Take that number, add 2, and then multiply by 5. We get new functions out of this. Now, not all functions are given this way, because we can give let's say analytically. So whenever I say analytically, or if I say a closed form expression, I mean typically what you're used to when you see a function. I mean actually describing in terms of our common language of f of x notation and writing out our sequence of operations. You literally explicitly write out the sequence of mathematical operations that this function is performed. So that is the way a function is given analytically. However, based on this pure math definition, we could still give functions in tables. We'll say tabularly, graphically, or we can give it as descriptions, either verbally or written. And well, this kind of goes back to this point. Well, what if we think of it as a sequence of operations, but given a table, given a graph, or given a descriptive information in terms of a function, it's not necessarily, you're not necessarily able to actually write down the specific sequence of mathematical operations. But again, this is an applied class, so yeah, maybe proper mathematical definitions. This isn't the proper mathematical definition of a function, and it doesn't quite cover these cases, but it kind of does. So especially if you're given information in a table or a graph, at least piecewise, and we will talk more about piecewise functions on Friday. Let's see, I should say a sequence of mathematical operations, generalize this, and maybe we should add at least piecewise given. That over different regions of our domain, there are different sequences we can apply on that domain to describe our graph, to describe our function. So of course, if you're given a graph, oftentimes you can reverse engineer the sequence of operations. If you're given a table, well, proper definition of a tabularly defined function is that the domain is only the values given. So for example, if you check out the book, there's a good example where it's like the population of the world at different decades. So 1980, 1990, 2000. Well, those specific data points given, we don't know what's going on in between those data points. We only have those specific data points given. And while it technically meets the mathematical definition of a function, there may not necessarily be a specific mathematical sequence of operations to define it. However, hopefully most of you guys are kind of thinking, well, there actually kind of is hidden there. So anytime we have tabular information, and when you think about statistically, anytime you take samples and sample sizes, once you guys have to take a statistics class, you'll realize that anytime we take data, anytime we're given data in tables, even though it's incomplete data, what do we like to do? we like to do what are called regressions. We like to assign a nice sequence of operations and assign a nice function to it, whether it's a polynomial, an exponential function, what have you. We like to do that to make predictions and to actually work with the data and to work with the mathematics that we have when we have these closed form expressions. So really in all these cases, even though it's not necessarily specific, it may not be proper. These are most commonly, we're going to have the tools of these analytic descriptions of what a function is, just a sequence of mathematical operations. On that note, in terms of generalizing what a function is, especially in these real world contexts, you can kind of think of it as something, or really anything, if you want to use that as a better word, that gets measured. Pretty much any real world quantity. This is kind of what a function is in the real world. Anytime you make a measurement, we assume that there's some sort of function going on. For example, if we want to measure the heights of individuals of a population, our dependent variable is then going to be the height that we measure. What could the independent variable be? Well, it could be a lot of different things, depending on how we set up our sample that we're doing. If we would like to use the techniques in this class, we would like our independent variable to be something that has a nice mathematical range. Let's say something like age. So age can be measured in years. It can be given in fractions. It's a nice, real number value that we can measure. And we could see perhaps a nice description. So just as kind of a terse example here, even though the data is going to be scattered, if we have height and then age, so let's mark it as time in years. Sorry, let me put that on the video screen. If I'm ever off screen, someone just speak up a little bit. Sometimes I'm not watching the YouTube video. But what is height going to look like? Well, on average, we might be able to assign some statistical average function that looks nicely enough as maybe some sort of logistic looking curve where people on average are born at a specific height. And as you age, you get older. And of course, that's going to taper off once you stop growing. So we are measuring height, and then it is a function of time. You can come up with a lot more examples like this. In quantum mechanics, if you want to measure the spin of an electron, there's some functions going on there. And I want you to start thinking about this, especially throughout the rest of your calculus career, because once you get into Calc 3, what we'll realize is that these values that we measure are not always real numbers. Sometimes the quantities we measure have additional information added into them. And we still want to think of a function as the same thing, even though the quantities and the values, the types of data that we are measuring might have different values or might have different mathematical data that's not necessarily a number. You can still kind of think at least there might be some sort of sequence hidden along there, or even a more complex sequence of mathematical operations that we want to use to describe that function. Okay, so that is it for today. We are getting a little bit behind, which is fine. This is all pre-calc review. On Friday, what we're going to talk about is, well, now what are our classes of functions? The general functions we should use are polynomials, our rational functions, exponential, logs, trig, are going to be our basic building blocks of functions. And then we'll probably spend a little bit of time talking about piecewise defined functions and some other pre-calc review of just general functions and what those entail. If we get too far behind, I will maybe make an additional lecture video and just have you guys watch it, or point you guys to some of the lecture videos I already have up on YouTube. And then come next week, it'll slow down a little bit. This is, again, we're all just blowing through the end of pre-calc here in like 3 days. Next week, we will slow down and actually get into calculus topics, where we're going to start to talk about limits and continuity. And then eventually we'll start to talk about derivatives.